Hey, today I'd like to talk about the binary search tree. The binary search tree is one of my favorite data structures out there because it pretty much combines the best of two worlds. It firstly combines um, easy extensibility, which is what you get when you use trees, because you can just append to new subtrees, so you don't have to reallocate all the memory, which is really nice. And you have also a very you have very good time complexity on all operations. So um, the average case, which is when just to clarify, the average case in terms of time complexity refers to when you have like 100 operations of the same type, and then you take all the time it took, and for those 100 operations to complete, and then you divide by 100. So it's the average case. So the average case is around log n, which means if you have like a million elements, right, it will only um, take at least uh, 10 lookups. So we can visualize this by looking it up. ln. Let's have it like 10, 100,000, 10,000, 100,000. You see, it's like 100,000. It's a million, right? It's a million elements. So even if we have to go through a million elements, we only are doing 13 comparisons, which is like very, very cheap. And this is like the big downfall of an array. If you want to search an array, you have to potentially search through all 1 million elements to know for sure that it is contained or it is not contained in the array. But in a tree, you only have to do 13 comparisons for a million elements, which is pretty good, right? And just to get an idea what a binary search tree is, I'd like to show you one, at least on Wikipedia. Wikipedia binary search tree, right? And this is how a binary search tree is structured. And as you can see, all the nodes on the right side are larger than those on the left side. Meaning, so if I say, okay, I look for a 5, okay, I see 5 is smaller than 8, so I go left. But 5 is bigger than 3, so I go right. And then I say, okay, it's 6. So I know for a fact, okay, 6 is larger than is larger than 5. So I go left again, and then I see it's a root node. It's a leaf node, meaning I know in just 1, 2, 3, 4. In 3 comparisons, I know that 5 is not contained within this tree, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 nodes, right? So as you can see, and this is unbalanced binary search tree. If it's balanced, it's even faster. This is what it's referred to as worst case, because if you have only one long stretch of nodes, which all follow one pattern, for example, all are smaller or all are larger, then you get essentially just a singly linked list. So this is the worst case. Anyways, um, this is what I was referring to the search and deletion complexity. And this is why I like the binary search tree. Um, this is my implementation of the binary search tree in Rust. And I mean, I am going to talk more about how you would implement it in Rust, not how you would implement an algorithm, because this is pretty self-explanatory. You just look at um, this diagram, and then you can pretty much implement it yourself. And besides, if you really want to do it, then you can just search for BST implementation in C, for example, right? And then you will find plenty of pre-made implementations so that you can just use them. Um, so this is more about a Rust thing and how you structure your data in Rust. Um, First of all, we have a binary search tree, and what you can see is that we have a node, and the node is sourced from the binary tree itself. The binary tree is just for the very generic one, which does not enforce any properties on the data. This is why I have implemented it beforehand and created a node. And we can just use that node in this implementation. And what you will see that a node in itself is in tree because it has data and it points to two different nodes, which in return may point to two different nodes. So you see that every node is essentially just a subtree. And this is done here. We have a root node, which is this node here, and it may or may not be populated, which is represented as an option in Rust. And then we have a usize, which is just a system length pointer sized integer, and this contains the current amount of elements stored in the binary search tree. Now, what you will see is that the binary search tree enforces this ordering property that we can observe here, meaning we have to enforce the OR trait. The OR trait, if you look at this, says it enforces equality in partial order. So it essentially tells us for you to use this tree, you must make sure that your types, your generic type T, is able to be compared to another type T for equality and for its ordering. So basically, if it's larger or smaller. The const function is pretty self-explanatory. We just create an empty tree, so we have none, and then we have a length of 0. That's that, and then we have insertion, and this is where it begins to become interesting, in my opinion. So what did I write? Insertion logic ensures that for every n in this case refers to every subtree level. Essentially, this is n0, this is n1, this is n2, this is n3. That for every n, L sub n is smaller than the R sub n, which is just the left and right subtree. This is what we have observed in this graphic. And yeah. And to achieve this, we must already battle with the borrow checker. The borrow checker, which enforces type safety and correctness of our programs at compile time, is very, very strict with us, and it does not let us do things that it cannot verify at compile time, which is why we have to do this duplication, which in case you avoid is optimized out. It is just for compile time checks, so this code will be compressed down into a much more efficient structure. But we need to be very explicit to tell the compiler, hey, what we're doing is absolutely fine and it's absolutely okay in our case. So what are we doing? We go and and look at our current node, which is the root node in the first iteration, and say if the root node is populated, we want to look at its value. So in this case, it's the 8, and then we look, is our new value that we're trying to insert larger or smaller? And this is then how we branch either in the left or in the right, into the left or right subtree. And then if the left is none, which means there is no new subtree, then we can create a new subtree, which is done here. In any other case, we just make the new subtree the new current, which gets then compared in the next iteration. Yeah, and then we just increment the length by 1. This is pretty much how things work, right? Yeah. And for those who are wondering why are we using current here, and you might think that we are assigning to the same data, that we're overwriting the same data twice because we are doing it here once and here twice. But this is just because I want to have a more maintainable code. And this is why I chose to make it purposefully a mutable reference to an option, which is in itself really pointless, but it allows us to do some funky stuff like changing this option to some other value, not the value contained within the option. So it's just a preference of mine. It is not really a best code practice, but it keeps code nicely aligned. Then what we have here are the min and max functions, and as you can see, that the outermost left leaf node is the smallest, and the outermost right leaf node is the largest, right? And this is what we can do here. We just follow. We go left, left. Can we go left? If we can't go left, then this is the smallest. Or we go right, right. Can we go right? No, we can't. So this must be the largest. And this is what we're doing here. So again, for reference, just use this graphic. The contains method is also very self-explanatory in my opinion, because it just leverages the properties of the binary search tree. In case we just are repeating the insertion logic, just that we don't actually care about if we have a leaf node or not. The only thing we're caring about is do we have a node which contains the searched value? If yes, then we return a true. If not, then it's a false. This is what we're doing here. Just as a sanity check, we do an assertion here because we are requiring from the implementer or from the user that he has or she has implemented a correct implementation of the ordering trait, which may or may not be true. This is why we do an explicit comparison here, just so that we have some reassurance that our tree structure is valid. And now, really, the most difficult part in every tree is how do you remove a node? Look, and this becomes very interesting in my opinion. We have a node, right? A node knows what data it holds, so this is the data field. So we can ask it, "Hey, node, can you give me your data?" And it says, "Sure, can do." And same goes for the left and right subtree. So if I ask a node, "Hey, do you have a left subtree?" It can say, "Yes, sure, I have a left subtree," or "No, I don't." This is encoded into this option here. But what if I want to know, okay, this is the node I'm trying to remove. So I have to ask the node, can you tell me where is your parent? And then if you look at this, the node itself doesn't hold any information about the parent. So it says, I don't know. And why do we need the parent information? Because the parent needs to point and set to the 3 to its potential left or right subtree, right? In this case, because if you're removing the 3, we need to point the 6 to, and we need the 8 to point to the 6, which in return needs to restructure its pointer to the 4, which in return needs to restructure it to 1, right? So the very tricky part in all tree data structures is removal. And the edge case in this case is the root node, because the root node itself doesn't have any parent, right? So it's impossible for us to know if to ask a root node where's your parent. So what we do is we check manually if the root node is the search node, we just manually remove it. In any other case, we have a find parent function, and this is where I have spent most of the time implementing it, and to make it look somewhat nice. The find parent function is taking a node, which is in this case the root node. So at this point, we already know that the root node is not the node we are searching for, but it could be either left or the right subtree. And what we're doing is we say, okay, if the target is smaller than the data contained in root, then we go to the left subtree. If not, we go to the right, right? And then what we do there is we just compare the subtree with the target node. And if those match, right? If the data of the new subtree matches with the target, we know we have found the parent of this subtree because this is the root of the current iteration. And this is what we're doing here. And for those who are wondering, why do I use two identical if-let destructuring syntax statements? And this is because the Rust compiler is very, very strict with us in terms of what is allowed and what is not allowed to be borrowed and for how long. As you can see, we have to explicitly say a tree node. So we say the Rust compiler, hey, I give you a root node, right? Which has some lifetime, which so it exists for some time, and I want you to give me, if you decide to give me a node, then I want this node to be valid for at least as long as the root node is valid. And because we have this constraint on our types, so if I were to say, okay, I'm gonna remove this, right? It's going to compile and say what it's going to say. Let's just look at this, right? We can just look at the compiler error message, and then we can see why Rust is such a good link. Oh my God. Oh my God. Come on, don't give me that right now. Why can I not make it larger? Okay, then we're going to do this really quick. Then we're going to do okay. Now we can look at what the error message says. Is we can say it already says because we have already defined it, so it knows where to look. But if we hadn't defined this, we would be in a world of pain because the Rust compiler says, "Yo, I don't know how long this lives for." So go figure. This is what the Rust compiler tells you. So in this case, it's really nice because I have already given it a hint. But yeah, what it says is this function returns function's return type contains a borrowed value. Okay, but the signature does not say whether it is borrowed from root or target. And this is a problem. We need to be very, very explicit in Rust to say who is dependent on whom and who is responsible for who, right? And this is why we have lifetimes. This is very, I mean, it paints your head. You really, really want to curse it. But once it works, you know it will work for eternity. And so we can just add the tree node lifetime and then all is good. And this is a function which is just has one simple purpose. It just allows us to borrow a value twice. Um, why do we need this? Because the Rust compiler is very strict, and it is not actually possible to at the time of this recording for Rust compiler to statically prove branching with lifetime. So basically, if statements. This is why we have also two separate if statements because it can prove or disprove if something happens or if nothing happens. This the compiler can prove, but if something happens with a lifetime or something else happens with a lifetime, the compiler can't prove that just yet. So we have to be very deliberate about it and destructure it into one that can or cannot happen, or in the other case, if we can do the same thing but just in the other direction. This is what essentially this is saying. And for those who remember that I said that it took me like forever to to make it look nice, I have actually collaborated with a friend of mine who has tremendously helped me improve the readability of it. And I can just paste my previous implementation of it. It works, right? It works. It doesn't complain, but you can see it's like you see how messy this is, right? And to be perfectly honest, this code that I wrote is if more efficient than the one my friend and I wrote together, because we are using a function pointer, which even if it's being inlined, it's still a jump, right? A jump is one instruction more, and it's potentially the reason why you would lose cache locality. So to be technically precise, this function is less performant than my initial function because it uses in-place traversal. So we use the same piece of memory. We have constant memory space complexity, and it is able to better utilize control flow. But to be perfectly honest, it looks very, very unmanageable to me. It looks ugly to me, and I'm all about aesthetics. I like beautiful things. And this is why I decided to run with this code, knowing that it is theoretically at least one clock cycle slower um, than this implementation. And I mean, now I'm talking about clock cycles. This is why I like low-level stuff, but a clock uh, cycle CPU, right, is Wikipedia come to rescue. You would like, oh, we just ask Intel, right? It's basically Intel. What can Intel do? Intel, so essentially, this is how a clock works. It sets pulses, and on each maximum or minimum we do something. But this is only from the physical perspective. But from the software perspective, clock cycle, it's a CPU cycle, I believe. CPU cycle, cycle instruction. Because every instruction takes at least one cycle, right? And this is what we can see. So we have uh, um, in practice, yeah, it theoretically takes 4 cycles to execute one instruction, but since modern CPUs have pipelining, we can execute like the moment we decode something, we can already execute its predecessor and so on, so on. So we get this very efficient cycling rotation, so that we have the amortized cost of only one instruction per cycle instead of four. But nonetheless, one clock cycle more is it's an improvement, right? So I'm not quite sure if I'm going to keep this or not. I mean, if it's really performance critical, here's the code, right? You can copy it, and then we will see from there how it goes. Yes, so essentially we with this function we can find the parent, and once we have found this parent, we can go back and say, okay, we have a parent, and then we find if the parent left or right child is the targeted node. And once we have found that, we just use the subtree removal function, which is essentially just this function that I have here, which is just remove node. And you can basically reuse it. And this is also very interesting. We see that we have um, a subtree, right? And let's say we want to remove the 0, so the root node. What is going to happen is we have to shift this left subtree one level up, but this has the problem that when we shift one level up in the left subtree, everything else becomes unordered. Plus, now that this has been shifted up, the right subtree of it must be reassigned to the and all its subsequent subtrees, and this begs the question. So this can, so the 1 can still point to the 3, but who is going to manage the 4, right? So the 3 must manage the 4, but who's going to manage the 6? In this case, it's going to be the 5, right? And this is what we have as a pattern. Only the left subtree is changed. So yeah, only the left subtree is changed. The right subtree, so the 2 and the 4, which are the right subtrees in our example, are not changed. And this we can check here. So if we have no nodes, so if it's a leaf node, we just return none. So it's pointing to nothing. If it's just having a left subtree, we just say, okay, point to the left, or if it just has a right subtree, just point to the right subtree. And this is what we are doing. As I said, the right subtrees must not change, and therefore we must search for the rightmost node, and this is done in this function, and this is the reassigning we are already doing here. We can see we have this recursive reassignment logic in rightmost. You can see rightmost is always changed, so we go zack, zack, zack. Yeah, then we just return eventually the left node, because this is what because the right subtrees don't change, just the left is changing, and the left is managing all the subsequent right subtrees. This is why we have to return the left. Again, this isn't really complicated. This is just a bit of, it's just theory heavy, but it is manageable. And then once we have this done, we have a clear function which just sets this to none. So we just delete all the subtrees, and then we set the length to 0. And the length in itself is just the length value. And then we have some test cases here. And just for good measure, we can just run cargo test, right? Or our test suite. Then we can see, all right, don't be this guy to me. All right, we can see I've implemented quite a lot of different data structures, but we can see here binary search tree, it works just fine. So yeah, this is a binary search tree. In the next episode, I am going to, where is it? Don't be telling me that I have lost it. Min-max heap, the min-max heap, which is also in a tree data structure, but it has the added benefit that it always has the smallest or the largest element, depending on if it's a min heap, then it's the smallest. If it's a large, it has a max heap as its first element. First element means it has constant time removal and finding, and we can look it up, right? Wikipedia, come to rescue. It is not very well documented as it seems, right? I mean, yeah, I mean, who is really implementing data structures as a hobby? This is also a question, right? They're difficult in most cases, but yeah. A min-max heap. Why do I implement a min-max heap? Because the min-max heap is the foundation for the Fibonacci heap. And this is where I want to go with the tree data structures. Come on, Fibonacci heap, right? This is where I want to go eventually, right? To the Fibonacci heap. And once we have the Fibonacci heap, I think a good next step would be the AVL tree. The AVL tree, mostly because AVL trees are self-balancing trees, and they have the added benefit, as I said, that while binary search tree, right? Come on, don't give me this binary While binary search trees and AVL trees are pretty much uh, on the surface the same. They have the same properties. There's only one added property that makes AVL tree, I believe, superior to the binary search tree, but it adds overhead. But it makes it self-balancing, meaning, as you can see, in a worst case, we have a linked list, right, of n time complexity, but the AVL tree is self-balancing, so meaning we pay at every time we do an insertion or deletion, we pay the balancing cost, which is a small cost. It's a constant cost, but it guarantees us that in the worst case we have our rate. Even in the worst case, we have log n time complexity. Um, this is, I mean, it really depends on your data, which you choose, because if you're only using, if you're only using like unordered data, that is very likely to have a widespread, like uh, from -100 to 100, then with a uniform density, then probably a binary search tree is better because just by the structure of your data, you get uh, almost perfectly balanced binary search tree. But if you have a very like skewed distribution of data, right? So if you have data that is really, really positive, so it's really around the 80 to 100 range, in the 80 to 100 range, but you have occasion like -10 or so, then you would have a very, very write heavy tree, and then you'd probably use a AVL tree to counteract the skew in data. And why do I use the AVL tree? Because the other option would be a red-black tree, and it was a pain to implement it in Python. I can tell you that much. And red-black trees are also self-balancing, and it just, I don't know, I really don't like them, and this is why I don't implement an AVL tree in Rust. Anyhow, I hope you've learned something and can use this knowledge in your life.